All right, guys. So we're back at it again. We're working on the 2026 brand new practice SOL um, that we've been working on. So we've made it to question number 22. Remember, this has 45 questions. Your SOL will have 55, but only 45 are graded. You don't know which of the 10 questions that you get are the ones that aren't graded. So make sure you treat everyone with, you know, thinking that you need to get this question right. Um, but remember, these 45 questions are based on the types and topics of questions that you should see on the SOL. I try to make them similar to SOL style questions. Um, but remember, you really want to go to the TestNav website and see and do a practice chemistry SOL in TestNav to see all the tools you get and really to see what you don't get. So what you need to have memorized or be able to write down on a scrap sheet of paper. Okay. So let's jump back into it. We were on question 22. So let me get there. I'll turn off my camera. You don't need to see me. All right. And we'll get to actually, we did question 22 and we're moving on to question 23. All right. So let's get there. All right. So 22, remember, this was the empirical formula. That adds up to around 30 grams per mole. 120 divided by 30 is 4. So multiply the subscripts by 4, and you get your correct molecular formula. Okay. So now we're moving on to the next one. All right. So we have a stoichiometry problem. So this, again, the types of questions we've been answering over the past few have been molar relationship questions. So that could just be as simple as calculating the molarity, or it could be a stoichiometry problem. It could be here's liters of a gas at standard temperature and pressure. How many moles do you have, right? So like mole conversions, what's the molar mass of something? Those types of questions. So here we got a combustion reaction. They give us the balanced equation, right? It says benzene. So if you don't know what benzene is, hopefully you know what these other three things are. So you realize that this, whatever benzene is, it must be this thing, right? According to the equation, if 3 moles of benzene completely burn, how many moles of water will be produced? So real easy, and you probably do it in your head because you already have moles. Remember, the first thing to do is take the given amount and convert it to moles, but we already have moles of benzene. According to our recipe, right, our balanced equation, we're going to get 6 moles of water are, are produced for every 2 moles of benzene that react, right? So all we have to do is take the moles of benzene that we have and multiply it by the ratio 6 to 2, right? Multiply by 6, divide by 2. So 3 times 6 is 18, divided by 2 is 9. So the answer is going to be 9, okay? So again, some Stuggy problems, especially if you already have the ratio and the numbers are kind of non-calculator friendly, you don't have to use the calculator. Everything's pretty much done for you, okay? But if we go back to the notes, if we want to see it, right, that's how we interpret our recipe, right? And we'll take 3 moles of benzene, we'll multiply it by the coefficient of the thing we want. So 6 moles of water go on top, and the coefficient of what we're looking for, 2 moles of benzene go on the bottom. That cancels out moles of benzene and gives you moles of water. Okay, so it ends up being 18 divided by 2, so 9. Now, if you wanted to, you could reduce the ratio 3 to 1, right? So 3 times 3 is 9. But you can keep it as is, right? Coefficient of what you're trying to get on top, the coefficient of the thing you already have on the bottom, right? And remember, they're mole ratios. So this 6 means 6 moles of water produced, and that 2 means for every 2 moles of benzene that burn, right? Okay. So, whoops. Let me go back to the actual test here, and we'll keep moving. All right. So here we have 25 grams of sodium chloride. They give us the formula. They remind us what sodium chloride is. Dissolved in enough water to make 1,500 milliliter solution and calculate the molarity. All right. So we just have to remember what molarity is. Molarity is moles of solute divided by liters of solution. So we got to remember to convert the milliliters to liters. So hopefully we can do that quickly. That's 1.5 liters. So our liters is 1.5. And we got to convert grams of sodium chloride to moles of sodium chloride. So sodium chloride is a compound that you should be able to come up with a formula for. So they didn't have to give it to us. But what do we need to do? We got to convert 25 grams of this compound to moles, so we have to divide by the molar mass. So it's nice that we have the formula for sodium chloride so we can calculate the molar mass by looking at our periodic table, right? So we'd have to go to our periodic table. One sodium is 22.99. One chlorine is 35.45. We add them up. The total of that is 58.44. So what do we have to do? We have to take the 25 grams, divide it by the molar mass of sodium chloride, which is 58.44. That'll give us moles. And then once we have moles, we'll just divide by 1.5 liters, and that will be moles per liter, which is molarity. Remember, capital M, which is molarity, is also called moles per liter, right? So let's see what we get when we do that, right? So again, molarity is moles over liters, right? This is a great formula to write down on your memory dump cheat sheet that you're going to make before you start answering questions on the SOL. Okay, remember, you don't get a formula sheet, so the things that you want to reference on a formula sheet, make sure you have them memorized, and make your own formula sheet when you get your scrap sheet of paper, right? Take 10 to 15 minutes and write down everything you can remember onto that, so you have it as a reference. So hopefully you write down capital M, which is molarity, equals moles over liters. So that reminds us to convert the milliliters to liters, right? Divide by 1,000, right? And then we got to take our grams and get it to moles. So we divide by the molar mass of sodium chloride. And then it's just the moles divided by the liters to make it molarity, okay? And you get 0.29. So the answer is that one, right? Or, you could just do it all in one-dimensional analysis. Grams to moles. Now you have moles on top. And then if you just divide by liters, now you have moles over liters, which is molarity. So same exact thing. So that would be our answer for this one. All right. But I'm sure if you did 25 divided by 1,500, maybe one of these is the answer. Or if you did 25 divided by 1.5, one of those is the answer, right? So remember what molarity is, right? And again, you don't get a formula sheet. All right, so here we have a solubility curve. Let me try to zoom in so we might be able to see it a little bit better, okay? And it says, according to the solubility curve above, what conclusions can be made about salts? So remember, the ionic compounds are salts. So Ki is a salt, sodium nitrate is a salt, KNO3 is a salt, ammonium chloride is a salt, this potassium chloride is a salt, the sodium chloride is a salt, the potassium chlorate is a salt. But like HCl, that's either a gas or aqueous when it's in water, right? Ammonia is a gas, SO2 is a gas, right? So they're not talking about those three. They're talking about the rest of them. All right, those are the salts. And what we should notice is as temperature goes up, solubility goes up, right? So for all of the salts except for this guy, KClO3. But or no, actually KClO3 is. Sorry, that was ammonia. Sorry. So this salt increases. The sodium chloride increases a little bit. The KCl increases, the ammonium chloride increases, the potassium nitrate increases, the sodium nitrate increases. So salts become more soluble as the temperature of solution increases, okay? And what you should understand is that's usually true for any solid that's dissolving in water. So even if it's not a ionic compound, like even if it was a sugar, solids become more soluble the warmer the water. And it's really about the motion of the particles, right? So warmer water, the molecules are moving faster, and the water molecules are able to break apart the solids better the faster they're moving, right? But the opposite is true for gases. So if they gave us the same chart and asked us about the solubility of gases, for gases, they become less soluble as temperature increases because it's harder to trap a gas in water when the faster the particles are moving. So colder soda, if you want to think of it this way, becomes takes more time to become flat than warmer soda, because colder soda it's harder for the CO2 to escape because CO2 is more soluble if the water's colder. But for solids, they usually become more soluble as temperature increases. So it's just maybe a good fun fact to know. Gases usually less soluble, solids usually more soluble as the temperature of your water increases. Okay. So yeah, it was the solubility of salts increases, solubility of gases decrease as temperature increases. Okay. Let's go to the next one. So we got the same solubility curve, but now we're going to actually use it. So let's understand how to interpret this. So if we, let's say we go to 70 degrees and then we go up to sodium chloride, it means at 70 degrees, a little bit under 40, so maybe like 38, 39 grams of sodium chloride. That's the maximum amount of sodium chloride that can dissolve if your solution is 70 degrees and you're only dissolving it in 100 grams of water. Now, 100 grams of water is about 100 milliliters of water, right? The density of water is 1 gram per milliliter. So when it says 100 grams of water, to visualize that, that's 100 milliliters of water. So not that big, not that much. So that's how you read this, right? So like, but if I'm at 70 degrees and I'm dissolving potassium nitrate, I would go up to potassium nitrate and I could say at 70 degrees in 100 grams of water, I can dissolve like 135 grams of potassium nitrate essentially, but I can only dissolve 38 grams of sodium chloride. They're both considered soluble, but remember solubility has varying degrees, like very soluble, somewhat soluble, not very soluble, that kind of thing, right? And if you dissolve that much, if you dissolve the maximum amount, then you're saturated, right? Okay, so a student is making a saturated solution of sodium chloride, so they're trying to dissolve the maximum amount, okay? And they're dissolving it at 90 degrees Celsius. We want to know how many grams of sodium chloride would be required to make a solution that is saturated if it's 200 grams of water. Okay, so that's the key. Remember, the chart says per 100 grams of water. So we'll go to 90 degrees, we'll go to sodium chloride, it falls right on 40. So the answer is 40 grams in 100 grams, but it's really going to be, all right, so again, to saturate a solution at 90 degrees, we need 40 grams of sodium chloride, but that's only for 100 grams of water. So if we double the water, we can double the grams. So it's going to end up being 80. All right, so that would be our answer there. Okay. All right, so again, let me see if I have any notes on that just in case. Yeah, so 90 degrees, it would take about 40 grams to saturate it. But that's 40 grams if you have 100 grams of water. But again, we had 200 grams of water, so we got to double that. So that's why it's 80. Okay. Saturated means the maximum dissolve. If you see a term like, I doubt you will, but if you see super saturated, that means you've dissolved more than what is usually allowed. So like if I'm at 90 degrees and I dissolved 60 grams of sodium chloride in 100 grams of water, then that would be super saturated. And then if you're below the line, you're unsaturated. You're not saturated yet. Saturated is the maximum that can dissolve. Okay. All right, let's keep on trucking here. All right, we go to this one. All right, so we got more solutions questions. So we got a solution of sodium hydroxide. So hopefully, as soon as you see that, you know that that's a basic solution. Okay. When you have hydroxide in solution, OH minus, right? That makes the solution basic. And so hopefully we can eliminate, a pH of 3 and a pH of 1 because that would be acidic. So it's got to be either 14 or 11. Okay. So remember, we take the negative log of the molarity of hydroxide that was given to us. The negative log of this is the POH, right? It's hydronium H3O plus or H plus that the negative log of that molarity gives you the pH. So this number, the negative log of this, gives us the POH and then 14 minus. So when you take the negative log base 10 of this, that's 3. So the POH is 3, 14 minus 3, 11. That means we have a pH of 11. So it's a base in solution and it's concentrated enough so that the pH is 11. All right, so again, if we go to reminders, right? So hopefully we go, oh, sodium hydroxide is the base, so we know it can't be A or C, right? We got to remember that it's just not, don't just take the negative log and think you have found the pH. If it's the negative log of hydroxide, that's the POH, right? The negative log of the molarity of hydroxide is your POH, and you just got to remember, once you find the POH, 14 minus will give you the pH. Okay, so we found the POH was 3, and then 14 minus 3 gives us our pH. Okay, so we go to the next guy here. All right, so here it's again more solutions. And this is a colligative property one. So it's asking which of these solutions would have the highest boiling point or the lowest freezing point. I'm trying to get 2 for 1 here. They probably won't ask this or that, but it's going to be the same solution. Remember, the more particles you have dissolved in your solution, the higher the boiling point it's going to be compared to 100 degrees Celsius, right? So water, pure water, starts at 100 degrees Celsius in terms of its boiling point. But then if you add stuff to it, you can increase it, the boiling point above 100. And then how far above 100 you go depends on how many individual particles you have dissolved, how concentrated it is, right? And the same thing happens to the freezing point, but it's opposite. You lower the freezing point. So the more particles you have, the lower the freezing point. So water freezes at 0, but if you dissolve things in there, like ions especially, you'll lower the freezing point, okay? And the more concentrated in terms of ions you have dissolved, the lower the freezing point. So we have to understand that when this compound and this compound dissolve, their ionic compounds, they break up into the ions that make up the compound. So this compound right here, aluminum nitrate, breaks up into 4 ions, 3 nitrates and 1 aluminum. Sodium hydroxide breaks up into 2, 1 sodium, 1 hydroxide. This is an acid, so you could think of it as breaking up into 2, H plus and acetate, C2H3 2 minus. But if you remember anything about this acid, it's a weak acid, so it doesn't completely ionize. So for every one of these that is in the solution, maybe you get 1.5 particles and stuff. So you could say 2. So this gives you 2, this could give you 2, this doesn't give you any, this gives you 1, right? This doesn't break up into smaller particles. This just breaks up into individual molecules that have this formula here, right? So really, you just take the concentration of the compound and multiply it by how many particles it breaks up into. This would be 1 times 1. This would be 1 times 2. This would be 1 times 4. This would be 1 times essentially 2. So which one has the highest number of particles? It's this one. It has 4 molar. It's the highest concentration of particles. All right, so if we go to my notes here, right, I'm reminding you, right, when salt's dissolved in water, right, this is what happens. It breaks up into 1 of these ions and 3 of those ions, right? This ionic compound breaks up into 1 of those ions and 1 of those ions. This acid could break up into 1 of these ions and 1 of those ions, but notice the sugar, when it dissolves, it doesn't change into smaller particles. It's just, is it solid? So it's these molecules surrounded by each other, or is it aqueous, individual of these molecules surrounded by water? So just 1 particle, okay? So because this has the more things dissolved in it, it's going to have the highest boiling point and would also have the lowest freezing point, okay? All right, we'll move on to the next. All right. So here we got the light bulb test. So it's talking about how strong of an electrolyte our solution is, and we get pH. Okay, so this is looking for a solution that would be considered basic and a weak electrolyte. Okay, so we can cross out the bright light bulbs because that would be a strong electrolyte. So we know it can't be HCl and we know it can't be NaOH. And then we could cross out this one, ammonium, because it has a pH of 5, so that would be acidic. So we need the pH of 9. That's basic, so it would be the ammonia. If they said basic and strong electrolyte, then our answer would be sodium hydroxide. If they asked for acidic strong electrolyte, it would be HCl, because that would be acidic pH and bright. And if they asked for a weak electrolyte and but acidic, it would be the ammonia, right? So the brighter the bulb, the better the electrolyte, right? You need ions in solution to be an electrolyte. So all those solutions have ions in them. But the one that's basic and weak would be the pH of 9 and the dim bulb, right? So HCl is acidic, strong electrolyte. Ammonium would be acidic, weak electrolyte. The sodium hydroxide, basic, strong electrolyte. And the ammonia is basic as well, but it's a weak electrolyte. It's also a weak base, and the ammonium is a weak acid. Weak acids are weak electrolytes. Strong acids are strong electrolytes. If you want to remember those, right? So, but that's not something I would worry about too much. Okay. So again, it's the ammonia. basic and weak electrolyte. Okay. All right, so here we have 5 grams of nitrogen reacts with excess hydrogen. So remember, when they tell us we have excess hydrogen, that means we have unlimited hydrogen, essentially. We want to know how much ammonia we can get in terms of mass. So it's stoichiometry. They have our balanced equation for us, so that's already done for us. So what do we got to do? We got to take the grams of nitrogen and first convert it to moles of nitrogen. Once I have moles of nitrogen, times 2 over 1 would give me moles of ammonia. And then once I have moles of ammonia times the molar mass of ammonia would give me grams of ammonia. Okay, so I probably have it worked out for you here. All right, so notice it's a 2-to-1 ratio. All right, we're going from grams of one thing to grams of something else. So remember, we have to first convert to moles. So remember, it was N2, so divide by 28.02, don't divide by 14.01. The ratio is 2-to-1, right? We want ammonia, so its coefficient goes on top. We have nitrogen, so its coefficient goes on bottom. And then this 17.04 is the molar mass of NH3. So 5 divided by 28.02 times 2 times 17.04, that will be our work. Now, you're going to notice that when you're taking the SOL, you don't need to write down a ton on your scrap paper, right? You don't have to show work. You don't have to show work. You don't have to do a lot of work for a lot of problems. But there are going to be a handful of problems where it would benefit you to write down. So use your scrap sheet of paper for your memory dump, all right? But then also ask for more paper if you need it, so you can work out questions like these, so you can actually write it out, right? Don't try to do this whole thing in your head, right? Use your scrap paper. Right? Be the kid that keeps asking the proctor for more paper. It's going to be annoying for the proctor, but they can deal with it, right? You're trying to do your best on your chemistry SOL, and sometimes you need to write things down. Okay, whoops, didn't see what the answer was. What was the answer? The answer comes out to be 6.08 when you do that math right there. Okay. All right, so that one. All right. All right, here, what is the mass of 2.5 moles of oxygen gas? All right, so they reminded us that oxygen was diatomic, but if they just said oxygen gas, you have to understand that is O2. So what do we have to do? We have to take the 2.5 moles and multiply it by 32, which we know, hopefully, by this point, is the molar mass of oxygen. Oops, so I got to go to this one. So we would just take 2.5 moles times 32 grams per mole, right? So if we needed to show our work, that's it. And it comes out to be 80. So our answer is 80 grams. All right. Okay. So here it says, what is the volume in liters? What volume in liters would 6.9 times 10 to the 24 molecules of carbon dioxide occupy at standard temperature and pressure? Okay. So what do we got to do? We got to take our number of particles of CO2, we got to divide by Avogadro's number to get moles, and then moles times 22.4 would give us liters, and we can always use 22.4 when we're at STP, right? STP is standard temperature and pressure, and it means you're allowed to use 22.4 liters per mole when you're dealing with a gas, all right? So understand that standard temperature and pressure means this. It means this is your temperature and this is your pressure, okay? It doesn't mean this, it just means you're allowed to use this. Okay, so what are we doing? We're going from molecules, which is particles. We got to convert that to moles, and then moles to liters of a gas at STP. Writing down a mole map might be a great idea for you for your SOL, for your memory dump. Okay, so mathematically, that's what we're doing. We're taking our number of molecules here. We're dividing by Avogadro's number. We're multiplying by 22.4. When we do our math, we end up with 257 liters. But if we round to 2 sig figs, that comes out to be 260 liters. All right. So let me go back to here. So 260 liters, right? So again, make sure you can put this number into your Desmos calculator. Make sure you can divide by Avogadro's number properly in your Desmos calculator. Make sure you understand how to input that. You may know how to do it, but if you can't execute the calculation with your calculator, right, you're going to have a bad day. So practice with Desmos. Practice chemistry calculations with the Desmos calculator so you get used to it, right? Okay. All right, we're continuing to go. All right, so Here, how many moles of hydrogen would be necessary to produce 4.97 moles of water? They give us the balanced equation, right? This one's a quick and easy one. The ratio for water to hydrogen is 2 to 2, 1 to 1. So if you want to make that many moles of water, it's going to take that same number of moles of hydrogen, right? So again, more stoichiometry, but again, we can do it in your head. If you wanted to do your stoichiometry steps, you would take the moles that you have, multiply by this coefficient, divide by this coefficient, and you end up with your answer of moles of hydrogen. Okay. All right, phase diagram. Remember, it always goes solid, liquid, gas. Always solid, liquid, gas. Solid, liquid, gas. Triple point, critical point. This temperature, critical temperature. Okay, normal, boiling point, and melting point means at 1 atmosphere, or whatever equivalent to 1 atmosphere is. So 760 millimeters of mercury, 101.3 kPa. Go to normal atmospheric pressure. This is the solid liquid line. So this temperature would be melting / freezing point. Go to the liquid gas line. This would be the boiling point, okay, / point of condensation. All right. So we got pretty much everything. Region A, again, that's solid, always solid. Okay. Whoops. Solid. Okay. Region B, that the rightmost region is always gas. That middle one is always liquid. Normal freezing point, what do we say? It looks around 60. Okay. It would also be the melting point. Normal boiling point, what do we say? 100. Critical temperature, critical point, go to the temperature, 110. And remember that point where solid gas, solid liquid, when all those 3 lines meet, that is called the triple point. All right. So those should be our answers for that. Okay. All right. So we're going to stop that video here. So that took care of questions 23 through 34. We'll pick it back up with question 35 with the last part of our video, 35 through 45. Okay. Again, now we're starting to get into maybe our current stuff, which is gas laws and KMT, which we talked about a little bit back in Unit 2, but now we're revisiting it. So make sure you focus on these last questions in particular, because that's the stuff we're currently learning, and it's going to be the stuff that you have the least amount of practice with before the SOL. So questions 35 through 40 are going to be very important to understand all of those concepts. Okay? All right. Have a great day. Good luck with your review.